Hello everyone, this is our heat transfer mini project video for group 9. The group members consist of me, Harvin Singh, Noor Irina Jiha and Lim Jiazen. Okay, for this mini project, the question that we got was to consider a fin heat exchanger and qualitatively discuss the effect that the thermal conductivity of the fin have on the heat transfer rate of the exchanger. We also need to discuss the effect of the heat capacity of the fin material onto the rate of heat exchanger. Okay, next, what is fin? Fin are actually extended surfaces on an object like this to increase the rate of heat transfer to or from the environment by increasing the convection heat transfer H. Next, there are many types of heat exchanger with fins. Okay, the first one, plate fin heat exchanger. It is a type of heat exchanger design that uses plate and fin chambers to transfer heat between the fluids. It is a compact heat exchanger that emphasizes the high heat transfer surfaces to volume ratio. This is the example of cross-sectional way of a plate fin heat exchanger. Okay, next, the plate fin exchanger uses a sandwich passages that contain fins like here to increase the effectivity of the unit. The design includes cross flow and counter flow to couple with various fin configurations such as the beside here, such as straight fins, offset fins with wavy fins over here. Okay, next is the fin tube heat exchanger. It's another type of heat exchanger with fin. It typically uses tubes that with fin attached to the outside of them. Like here, there's a fin attached to the tube. Okay, the additional heat transfer surface area due to fin increases the heat transfer rate as we discussed before. So this is often used in power plants and industrial dryers. Okay, next, this is the example of the fin tube. Over here, this is the one of the application in heat exchangers. Okay, next, the application of heat exchanger with fins. It is variously used in car radiators to increase the heat transfer rate between the car radiators and the air outside. So this is used. Then this is the evaporating coil for air conditioning unit. This is variously used in air conditioners.
Fin tube heat exchangers, also called industrial radiators, have a wide application in the process industry for a variety of applications, be it gas cooling, hot air generation, cooling of a process liquid, and so on.
The essential component in a fin tube heat exchanger are the fin tubes, where seamless metal tubes are wrapped around with transverse fins that helps increasing the surface area necessary for transfer of heat across the wall of the tubes. In a fin tube heat exchanger, it is the process liquid that is pumped through the tubes from one end, which then moves through successive rows of tubes to the other end. During the process, depending on the application, the liquid either picks up heat or loses the heat to the air or gas on the other side.
Thermal conductivity. Thermal conductivity is denoted as K. It is a property of material to conduct heat, and it is evaluated primarily in terms of Fourier's law for heat conduction. There are some assumptions that had been made in this question, which is the constant. First, the mass equal to 10 kilogram, H equal to 5 watt meter Kelvin, area equal to 10 meter square, length equal to 10 meter, temperature surface equal to 80 degrees Celsius, and temperature ambient equal to 25 degrees Celsius. The equation used in this question is this equation. So first of all, we calculated R first. R is given by this equation 1 over, okay, so we have K, we have area, we have H, we have M, and we have L. We insert everything and then we get R, first value of R for this value of K, which is 0.0004. After we get the value of R, so we just need to focus on this equation. We have the temperature difference, which is equal to 55 degrees Celsius, T1 minus T2, so we get 55. Next, we calculate Q, temperature difference divided by R, so we get about 137500 joule per second. Then we just need to increase the value of K, increase the value so that we can get the value of Q. To determine the relationship between K and Q. So then we plot the Q, heat transfer, versus thermal conductivity. So from this graph, we know that thermal conductivity is directly proportional to heat transfer. When we increase the value for thermal conductivity, the value of heat transfer also increase. So again, thermal conductivity is directly proportional to heat transfer.
Hello guys! So today I'm going to explain about the heat capacity. So first of all, what is heat capacity? Heat capacity is the ability of a material to store the heat. And the higher the heat capacity, the higher the amount of heat stored by the material. Heat transfer usually varies inversely with heat capacity. So I will give an example here. Heat transfer will decrease when the heat capacity increases or vice versa. And the thermal diffusivity is the ratio of thermal conductivity to the heat capacity. It says that how slow or how fast the heat is transferred in the material. Usually, the thermal diffusivity is directly proportional to the heat transfer rate. Since that the heat capacity appears on the denominator, so the heat transfer is inversely proportional to the heat capacity. So now I'm going to show that the result we have done. This one is the Q, which is the rate of heat transfer, and the C is our specific capacity, our heat capacity. And how we get the C? The C is get from the Q, the heat transfer rate, over the delta T, which is 55. The delta T came from 80 minus 25. And based on the result on the table, our group also plot the graph, which is the heat transfer rate versus the capacity, the heat capacity. And this one is the graph. So that's all from me.